Hello everybody, I welcome you all to NKS Geology class. In the last class I was discussing about the interior of the earth. In first part I have discussed about the crust. Now I will discuss about the mantle. Mantle is the second largest layer of the earth, which is the source region for most of the earth's internal energy, and these forces are responsible for ocean floor spreading, continental drift, orogeny, volcanism and earthquake. It extends from most discontinuity, which separates the crust from the mantle at a depth of 33 kilometers. So from most discontinuity up to 2900 kilometers is the mantle. So at 2900 kilometers there is another fast order break which is called as Gutenberg discontinuity. So the earth that exists between 33 kilometers or below Mo up to Gutenberg discontinuity is the mantle. It accounts for 83% of the volume of the earth, 68% of the mass. Compositionally it is enriched in magnesium, less in iron, much less in silicon. MgO is around 30 to 40%, FeO 8 to 10%, SiO2 40 to 45%, Al2O3 4 to 5%, calcium oxide 3 to 4%, and hence it represents ultra basic or periodic in composition. And these are the dominant minerals: olivine, pyroxene, spinel, plagioclase, garnet. These are the dominant minerals in the mantle. And the density goes from 3.3 to 5.7 at the mantle core boundary. And the mantle is divided into several parts. The upper mantle, which goes from Moho to 660 kilometers, and upper mantle is having a part of the lithosphere. Lithosphere is crust plus upper part of upper mantle. So a part of the lithosphere is coming in the mantle. So below lithosphere, so lithosphere goes up to a depth of 100 kilometers from the surface of the earth. It is breakable, rigid, strong, and it has made the plates, lithospheric plates. Below lithosphere there is asthenosphere, which is a layer virtually having no strength to resist deformation and is noted for plastic flow and convection as a mode of transfer of heat and plate motion. Its thickness is from 100 kilometers to 660 kilometers, and it presents different layers. The upper layer is low velocity zone, LVZ, which is extending from 100 kilometers to 250 kilometers. Here the periotic rocks are in partially molten state, because of which the seismic waves drops. Velocity decreases, that's why it is known as low velocity zone. And this low velocity zone is not detected under Precambrian sealed areas under the continents, but they are seen in oceanic crust, below the oceanic crust. And the upper part, or it is, so this low velocity zone is not there in case of Precambrian seals. It is also, this LVZ is also called as a part of Gutenberg layer or anomalous upper mantle. This zone is noted for low Q and high electrical conductivity or high attenuation or high weakening of seismic wave velocity, because it is in semi liquid state, molten state, partially in molten state. That's why the velocity of seismic waves is low. So high attenuation of seismic waves is there, or high weakening of the seismic waves is there in this zone, LVZ, low velocity zone. After low velocity zone, from 250 to 410 kilometers, there is steady rise in seismic waves. Velocity rises. It is known as the rigid zone. And Gutenberg layer is extending from below the Moho to 410 kilometers. This is Gutenberg layer. Then after this, after 410 to 660 kilometers depth is the zone where there is rapid rise of seismic velocity, and that's why it is called as the transitional zone. And otherwise also it is otherwise known as the Galitzin layer, noted for high seismic velocity, and it might be because of the presence of very dense minerals in the transitional zone. In the lower mantle, it extends from 660 kilometers to 2900 kilometers. Some authors say that the transitional zone, which is thought to extend from 410 kilometers to 660 kilometers, some authors say that it is extending from 410 kilometers to 1000 kilometers, and up to this depth the upper mantle goes. If you take, but generally it is accepted that the upper mantle goes up to a depth of 660 kilometers. So lower mantle begins from 660 kilometers and extends up to 2900 kilometers. And this lower mantle is divided into two layers, D1 layer and D2 layer. D1 layer is the upper layer which goes from 660 kilometers to 2560 kilometers. This is solid, and there is gradual rise of seismic velocity in this zone, and it is followed by a lower layer between 2560 to 2780 kilometers depth, that is D2 layer. It is the anomalous low velocity zone because of the origin of pockets of magma at this zone or formation of formation of mantle plumes. And below it, below 2780 to up to 2900, there is a constant velocity layer, and that is known as DAMS, constant velocity layer. And if we take into account the velocity, P wave velocity, it shows a rise from 8 km to 13.8 km per second at the mantle core boundary. S wave goes from 4.5 km to 7.5 km per second in the lower layers, and the velocity of P wave falls from 13.8 to 12 km per second in this zone, 2560 kilometers to 2780 kilometers in this zone, which is the D2 layer. And this D2 layer, which is known as ultra low velocity zone, is identified by Williams and Garnero in 1996. Besides that, we have many second order breaks which are not universally present within the earth. The presence based upon gravity, the breaks, they are present because of the change in value of G, change in value of seismic waves. We have a break at 950 to 1000 kilometers, which is known as a break in the mantle, repeated discontinuity is called. There are other second order breaks, such as density break at a depth of 80 kilometers, gravity break at a depth of 150 kilometers, and seismic break at 410 kilometers. So these are some of the breaks which are present in the mantle, and the D2 layer is noted for its ultra low velocity zone because of the mantle plumes. Where there is no mantle plume, the velocity, the seismic velocity is found to go up to 13, more than 13. But where the mantle plumes are there, the velocity reduces to, or it becomes 12 kilometer per second. And if we, so if you analyze the composition of the mantle, it shows that it is made up of denser minerals, olivine, pyroxenes. They have been transformed with depth to very denser minerals. There has been polymorphic transformations. Composition remaining same, they have been made more dense, more compact. The structure continued to become cubic or the spinel structure, which is dense structure, as a result of which the seismic wave velocity is found to increase with depth. And if we study the rock types of the mantle are said to be pyrrolite. It is pyrrolite. It is combination of 3 parts of ultramafic rocks of dunite and 1 part of basalt. The mixture is called pyrrolite, or it is generally called as peridotite. And this peridotitic rock is the main composition of the, or pyrrolite is the main composition of the mantle. And these mantle rocks, they show a depletion, or they show depleted peridotite below the continental crust. And this depleted peridotite contains pockets of eclogite segregations. And the depleted peridotite below the oceanic crust contains upper layer of strongly depleted Harzburgite, which is olivine pyroxene rock. And below this, there is less depleted lergolite. So main rock of the mantle is peridotite, and we can say it is pyrrolite, which is a combination of 3 parts of dunite, 1 part of basalt. Mixture is peridotite. And the place where the magma has been generated, that shows depleted peridotite. And if we take into account the mineralogy, olivine changes to beta olivine to gamma olivine, particularly in the transitional zone, where the velocity of the seismic wave shows an abrupt rise. It is only because of the conversion of alpha olivine to beta olivine to gamma olivine. Gamma olivine is very compact. It is showing spinel structure. Beta olivine distorted spinel structure. Alpha olivine orthorhombic structure. So this is the conversion of polymorphic transformation of olivine. Similarly, there is transformation of pyroxenes. The orthopyroxenes and clinopyroxenes, they show a change with depth, and they form solid solution with garnet to form meteorite within the zone of within the transitional zone. Meteorite is being produced in the transitional zone from the pyroxenes, making solid solution with the garnets. So olivines show conversion from alpha olivine to beta olivine to gamma olivine within the transitional zone, and pyroxenes, they show change to meteorite. And below the upper mantle, below 660 kilometers depth, they all change to perovskite, magnesioustite, calcium perovskite. These are the major minerals which are produced in the lower mantle. these are still denser rocks, denser minerals with simpler composition, simpler structure that may be spinel structure. So, the mineral transformations in the mantle can be classified as the from Moho to 410 kilometers depth or below before the beginning of the transitional zone. The rocks are pyrrhotite, euclogites. The minerals are olivine, pyroxene, and garnet. And the olivine is alpha olivine with orthorhombic structure. Orthopyrogens, clinopyrogens, they change to garnet gradually and produce garnet pyrrhotite. Aluminosilicates such as plagioclases present within a depth of 50 to 90 kilometers, they become spinel 90 to 100 kilometers, garnet at greater depth more than 200 kilometers. So in the transitional zone, there is seen very abrupt rise in the seismic velocity because of the formation of denser minerals such as alpha olivine changes to beta olivine or wadlesite. Or where the magnesium is 6 or in 8-fold coordination, silicon is in 4-fold coordination. Pyrogen changes to garnet, that is meteorite, having this composition. And at a depth, so this begins at a depth of 410 kilometers. Alpha olivine changes to beta olivine, garnet to meteorite. But at a depth of 520 to 600 kilometers within this range, beta olivine changes to gamma olivine, which is ringwoodite, having spinel structure or cubic structure. With magnesium in 6 or 8-fold coordination, silicon in 4 or 6-fold coordination. A garnet change to ilmenite structure, having composition MgSiO3. Magnesium silicate with ilmenite structure. After 660 km depth, all these minerals, they change to 3 general phases. What are they? These are ferropericlase or magnesiostite, then magnesium perovskite and calcium perovskite. Besides this, there is periclase and other phases, other mineral phases which are stable in the lower mantle. They are stishovite, corundum, ilmenite and ferrite. So these are the minerals. So we can say their alpha olivine dominates in the upper mantle, and in the transition zone below 400 kilometers, 410 kilometers depth, the alpha olivine changes to beta olivine or wadlesite. At 520 kilometers, it changes to gamma olivine or ringwoodite, and there is a seismic break. Seismic velocity rises, and at 660 kilometers discontinuity, there is still rise in the velocity. At lower mantle, they all break to perovskites, which are brickmanite minerals and ferropericlase. So this is all about the mantle, and in my next talk I will discuss about the Earth's core, which is the innermost zone of the Earth and which contains iron that is responsible for the Earth's magnetic field. Thank you all for your patient hearing.